Okay, guys, I am so sorry that I'm not there today, but circumstances have prevented me from being there. So hopefully you read Module 5, and we're going to go over the first half, which is pages 172 to 184, okay? And it's dealing with polyatomic ions and molecular geometry. Okay, so previously, you guys learned how to create Lewis structures for molecules, right? Well, this is just the beginning, as many molecules are more complicated. They're important for lots of chemical processes. And so it's kind of like learning about shapes when you're younger. Okay, when you first start learning about shapes, you learn about circles, and you learn about squares and triangles and so forth, right? But when you're first learning about them when you're younger, you're learning about them in a 2-dimension, right? But in real life, in the real world, most things aren't 2-dimensional. They're actually 3-dimensional. So you're dealing more with spheres and cubes, right? Things like this. So most molecules actually have a 3D shape, and it's an important part of understanding how they react chemically with one another and understanding their shape. Okay, so I'm hoping that you guys end up becoming experts at 3D molecular structures. Okay, so let's look at a molecule of sodium chloride. Okay, so when I have sodium in the Lewis structure, and then I have chlorine, if I have the Lewis structure. Now, typically I'd go 1, 2, 3, 4, right? And fill it in that way, but I don't need to do that right now. Okay, so when a molecule of sodium chloride forms, sodium gives its single valence electron to the chlorine atom, okay? So basically, this valence electron is going to come over here, which is going to make sodium happy, and it's going to make chlorine happy, right? And so then that's going to give your sodium a plus charge because it lost its electron, and it's going to give a minus charge, right? Because it gained an electron, okay? So when this process happens, you are creating 2 ions. So there are other ways that ions can form, okay? Sometimes many atoms get together in a group, and that group can lose or gain electrons, and they become ions made up of more than one atom. This is a polyatomic ion, okay? So polyatomic ions are ions that are formed when a group of atoms gains or loses electrons. And you guys know I write electrons like that. Okay? So that's what a polyatomic ion is, and you need to know this. You need to know this definition. So let's look at how this happens. All right. So if I have a hydrogen atom and I have an oxygen atom, okay. So the way that these guys can come together is you can form a covalent bond, right? And it's going to look like this. That's with one single covalent bond. But this is kind of problematic, right? while my hydrogen's happy because it has 2 electrons, it's in its ideal state, my oxygen is not happy. It has 7 valence electrons, not 8. So you can assume a stable molecule of this cannot exist, okay? Because this is not an ideal state. I hope that makes sense. So the oxygen wants another electron, right? So to have an ideal state, there needs to be another atom that's willing to give its electron up. So let's say there were a sodium atom over here. Well, it could donate its single valence electron to the oxygen. This would be happy, this would be happy, and now this would be happy, right? So this now has a negative charge, right? It gained an electron. My sodium now has a positive charge, right? Because it lost an electron. So everyone's happy with their ideal electron configurations, and opposite charges are attracted to each other, so everyone's happy with that, okay? Okay, I hope you can see that OH is a polyatomic ion, okay? The 2 atoms, oxygen and hydrogen, share the negative charge from the single valence electron that sodium donated. Okay, this is a polyatomic ion right here. Okay, so when this happens, this is not an oxide ion, okay? It also isn't a hydride ion. This polyatomic ion is called hydroxide, okay? So this is a hydroxide ion. And when the hydroxide ion and the sodium ion are together, we get an ionic compound called sodium hydroxide, okay? And how you would write this in its chemical form, you would write sodium hydroxide, okay? And you have to keep the oxygen and you have to keep these 2 together, the hydroxide together, because they are connected with a covalent bond, and so they have to be next to each other when you're writing the chemical formula. Okay, it's not going to be hydrogen over here, sodium over here. This is your polyatomic ion, and it needs to be kept together. So by definition, any ion that has more than 1 atom in it is a polyatomic ion. Okay, let's look at another one in case you guys are confused or wondering what's going on. Okay, so I want to look at another one. I want to look at a carbonate ion, okay? In a carbonate ion, I have 1 carbon and I have 3 oxygen, and these are their Lewis structures. And remember that I add up the total valence electrons. So I've got 6, 12, 18, plus 4, there's going to be 22. So then when I'm putting my formula together, this is what I get. My carbon is happy, 2, 4, 6, 8. This oxygen is happy, 2, 4, 6, 8, ideal state. But this oxygen and this oxygen are not happy. Okay, 2, 4, 6, 7. 2, 4, 6, 7. They both have 7. The pair, the extra pair of electrons, are evenly distributed between the 2 oxygen. And so this is the Lewis structure that gives. Okay, so the oxygen here and the oxygen here are both needing to gain an electron to have an ideal configuration, right? I can't add any more double bonds to carbon because carbon already has 8 electrons. It's already happy, right? So let's say that I have 2 potassium atoms hanging around. So I have a potassium over here, and I have a potassium over here. Well, that would be great because this potassium could donate its valence electron up here to make this oxygen happy, and this one could donate its valence electron here to make that oxygen happy. Okay, and so that would leave you your potassiums with a positive charge. And then I'm going to put this in parentheses because that's my center molecule. And so then this, I redrew it. I don't know why I'm redrawing it, but is going to have a -2 charge, right? Because it gained 2 electrons. This is a carbonate ion, and its molecular structure, chemical, okay, that's how you would write that. Okay, and an ionic compound is formed from this when the 2 potassiums are around. It's going to give us potassium carbonate. And this is what it looks like. Potassium. Okay, so there are some common polyatomic ions that you need to know. You're going to need to know the name. You're going to need to know the molecular formulas. You're going to need to know the overall charges of them, and they are located on page 155, table 5.1, right there. Okay? You don't need to know the Lewis structures of these guys. I just did that for the previous few examples because I wanted you to see why they form the way they do. Okay? But you are going to need to know the names, the formulas, the overall charge, okay? And the reason why you need to know them is so that you can figure out chemical formulas of the ionic compounds that they are a part of, okay? And the more you use these, the easier they're going to be to remember. Another thing that I want to point out on this chart, okay, you see this ending? You've got nitrate and nitrite, and over here you have sulfate and sulfite right there. Whenever you have the ATE ending, it means there's more oxygen atoms than when there's the IT ending, okay? And that lines up. So nitrate, right there, you can see it's NO3. Nitrite, it's NO2, okay? There's less in the ite than the eights. Hope that makes sense. Okay, so let's do another example together. If I said, what is the chemical formula for calcium nitrate? Okay, so what is this chemical formula? So I know from my table, right, that I need to know this nitrate is NO3 with a minus charge. Now, if I look at my periodic table and I find calcium over here, calcium is in group 2A, right? It's going to give up 2 valence electrons, which will give it a positive 2 charge. Okay, remember what you do when you balance. You drop the charges and you reverse the subscript in order to get the chemical formula. So this is going to be a 1. So basically be like as if you had calcium here. And you reverse the 1 here and the 2 here. And then when we have a 1, you don't have to keep it. So it's going to be, okay. parentheses matter because you need to know that there's two of these ions, okay? The nitrate is a single item. That's why it's in parentheses. You don't have nitrogen and then oxygen. You have nitrate, which is an O3, and then you have two of them. So that's why you have to have the parentheses to distinguish. I hope that makes sense to you guys. All right, let's do another example. Hopefully this will help you as we just truck through. So what's the chemical formula for aluminum dichromate? All right, so aluminum. Hopefully you can see right here that it's in group 3. Excuse me. It's in group 3A. So it is going to give up 3 valence electrons, which will give it a +3 charge. I know from the table. And it has -2 charge. I know that from my previous table, okay? Remember, you guys are going to have to know that. So then you just drop your signs and you switch your subscripts. That's going to be aluminum 2. And you're going to have 3 of these. That's why you need the parentheses, okay? Keep the dichromate ion in parentheses so it's evident that it's a polyatomic ion, okay? So in this ionic molecule, there are 3 dichromate ions and there are 2 aluminum ions. And let's do one more so you can see one different type of example. What's the chemical formula for copper 1 acetate? Okay. So copper, okay. So according to the name, it tells you what charge that copper is going to have, right? It's going to have a +1 charge because it's copper 1. Then you've got your acetate. Okay, you drop your charges and you switch your subscripts. They're both 1 in this case. Okay, I don't have to have parentheses in this formula because there's only 1 acetate ion. If there was more than 1 acetate ion, I would need to have the parentheses, but since there's only 1, I don't. Okay, hopefully you guys followed that. All right, so now we're going to jump into molecular geometry and the VSEPR theory, okay? So we need to start discussing more about covalent bonds, and we need to start looking at the molecules in 3D space. So remember when I talked before, instead of looking at it as 2-dimensional, we need to start looking at them more as 3-dimensional, okay? So molecules are in 3D space, so they have length, they have width, they have depth. But because we're working on 2D format, we're working on paper, there's a convention to showing covalent bonds in 2-dimensional so you can visualize them as a 3D object, okay? So if I'm looking at, let me use methane. Okay, if I'm looking at, that's the example the book shows. If I'm looking at the, okay, so remember that the covalent bonds are representing a shared pair of valence electrons, okay? And because of that, because there's shared pair of valence electrons, if they weren't if they didn't look like the bonds. You need to remember that there's pairs of electrons there. So they're all negatively charged, okay? Like negatively charged, negatively charged, negatively charged, and negatively charged, right? So because of this, because there's negative charge here, negative, 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 remember, like charges repel each other, right? So they want to be as far away from each other as possible, which means it's not going to look like this, where there's 90-degree angles in between each one. They want to be further than that. So it's actually going to be a tetrahedral. And let's see if your book, right. So it's actually going to be, okay, hydrogen. Okay, so it's actually going to be a tetrahedral with the angles, instead of being 90, the angles are going to be 109 degrees because they want to be further apart. Okay, and so to show what's going on here, we use a solid line, okay, to show chemical bonds in the plane of the paper. So these are in the plane of the paper. We use a dash line. That means that the bond is going behind the paper, okay? So it's not circled, but I've got one here. This would be the plane of the paper. This would be, and then I've got one going, it's hard for me, one going behind, okay? And then the triangular line right here, it represents a bond that comes out of the paper. Okay, so this is my 3D shape. Got one here, one coming out at me, and then one going behind. Okay, this tetrahedral shape is one of the fundamental shapes molecules will take on. Okay, and in this shape, there's 4 covalent bonds, right? I have 4 covalent bonds in this shape. Now we can predict molecular shapes using the VSEPR theory. So VSE. VSEPR theory. Okay, and this stands for valence, shell, electron, pair, repulsion. Okay, and this theory basically means molecules will take whatever shape that keeps the valence electrons of the central atom as far apart from each other as possible, because they all have like charges and they're trying to repel each other and get away. So the molecule's going to take the shape that keeps the valence electrons of the central atom as far apart from each other as possible. Okay, so there's other shapes that molecules can have besides this tetrahedral one. Let's look at an ammonia molecule. I believe this is in your book, so. Okay, so around the central atom, we have 3 bonds and a non-bonded pair of electrons, right? So these electrons are closer to the nitrogen atom than if they were bonded, okay? So they end up exerting a bit more force on the bonds, moving them a bit closer together, okay? So the non-bonded pair is right on top of the nitrogen atom. So in this shape, the angle isn't going to be quite as far away. So before we had the 109 degrees, this one is going to end up being about 107 degrees. It's only slightly because of the one unbonded pair. So let me show you. That one's going in the back. This one is coming in the front. And then you have this one still on the plane. So this angle is about 107 degrees. Okay. So I still have this one coming forward. I have this one going back. And then I have this one in the plane of the paper. And then I have my unbonded pair. So you're going to need to know not only the molecular shapes, but you're also going to need to know the bond angles. Okay. So this shape is like a pyramid. So it's called pyramidal shape. Okay, so the tetrahedron, it was composed of 4 bonds, right, with angles at 109 degrees from each other. The pyramidal shape has 3 bonds, right, at angles of 107 degrees from each other. And then they have that unbonded pair of electrons. All right, let's look at water now. Okay, so what's going on with water? There are 4 electron groups. 1, 2, 3, 4. 2 of the electron groups are bonds, right? 2 of these electron groups are bonded. And 2 electron groups are unbonded electron pairs. So what happens when you have this situation? You end up with a bent shape. And 105 degree angles. So it's going to look like something like that. Okay. The bond angles are a bit smaller because of the 2 unbonded pair of electrons. Just as it went from 109 to 107, when you have another pair, it gets them even a little bit closer, so then it goes down to 105. Okay, that should make sense if you're following along. So far, all of these shapes were basic tetrahedral shapes, right? So now let's look at a different one. What if I have something like this? Okay, so I'm always looking at the groups on the central atom. All right, so this is an electron group, right? It's a bond. This is an electron group, it's a bond. And this is an electron group, it's a bond. This is not considered 2 electron groups. Okay, this double bond is considered as 1 electron group. It's technically a bond that's doubly strong as a single bond. Okay, so in this, there are 3 electron groups. Okay, 1, 2, 3. And they're getting as far apart in 3D space as they possibly can. And so, got our central. It's going to look something like this. And my angles are going to be 120 degrees. And it's going to be a triagonal shape. Actually, I think just trigonal shape. Sorry about that. Okay, just trigonal shape. All right. Now what happens, let me give you another shape. Let's do linear shape. Okay, when you look at something, okay, when I look at something like this is going to be a linear shape where the angle is 180, right? So to determine the overall 3D structure of molecules, you need to determine how many groups of electrons are around the central atom. Okay, you draw the molecule, the Lewis structure, then you count the number of electron groups around the central atom. If there are only 2 groups around the central atom, then the molecule is going to be linear. With 180-degree bond angles. Okay, if there are 3 groups, it has to be and with 120-degree bond angles. Okay, if there are 4 groups, it will form a tetrahedral or one of its 2 derivatives. Okay, so if all the groups are bonded, let me give you the examples. If all the groups are bonded, so there are 4 groups, but all of them are bonded, it's going to be a tetrahedral with 109-degree bond angles. Okay, if it's in the example before, if you have 4 groups, 3 are bonded, and 1 is an unbonded electron pair, it's going to be pyramidal with 107-degree bond angles. And lastly, if you have 4 groups, 1, 2, 3, 4, where 2 are bonded and 2 are unbonded electron pairs, you're going to get bent with 105-degree angles. Okay? All right, so the last thing I want to do is go over some examples with you. So this question says, what is the shape and bond angle of molecule PHCl2? My total valence electrons. Okay, my total valence electrons is 20. So when I group these together, I have the most unbonded pairs here. Phosphorus, I'm going to do H here, Cl here, Cl here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, everybody's happy. So I have 4 groups around my central atom. Remember, that's what we're looking at. I have 4 groups of electrons around my central atom. 3 of these groups are bonded, and 1 group is an unbonded pair. So you should know from what I told you earlier that this is going to be pyramidal with a bond angle of 107. And if I were, it asks for the shape. So I'm going to put this here. Then I'm going to have one going back with the dotted lines. And I'm going to have one coming out towards me in front. And then I can't forget my unbonded pair. Okay? So this is my shape, pyramidal 107. That's a picture of it. Let's do another example. What is the shape and bond angle of a SiO2 molecule? Okay, silicone. So to do the process before I work it out, valence electrons for time's sake. Okay, everybody's happy in that structure, so I did it right. Count my valence electrons. And I have, how many groups of electrons do I have around my central atom? I hope you only say 2. This is not 4, it's 2. Remember, a double bond is counted as 1 group. It's doubly extra strong, right? So there's 2 electron groups, which means this is going to be linear, 180 degrees, and that's what it looks like because it's linear. Okay, and let's do one last example. Determine the shape, SF2 molecule, give its bond angle, and draw a picture of it. Okay, so I hope as I'm going through this, you know what I'm doing, because we kind of did this last chapter. If you're confused, let me know, and we'll work backwards and make sure that you understand what I'm doing here. Hopefully, as I'm writing this, you know exactly what I'm doing and why. Okay, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And if you count up my valence electrons, it's all correct. So again, what do I look at? Central atom. How many electron groups are there? 1, 2, 3, 4. Now, how many of those are bonded? 2 are bonded and 2 are unbonded. So what does that mean? It means this is going to be bent. It's going to have bond angles of 105 degrees. And then if I draw it, I can draw it kind of up like that with bent, and then kind of down like that. Okay. When determining the molecular shape, remember you're going to focus on the central atoms only for this course. Okay. The other electrons around the non-central atoms aren't going to affect the shape for what we're talking about. Okay, that's it. That's it, guys. If you haven't already, please turn in your tests to Mrs. Hughes. I'm going to collect them from her. If you're watching this at home because you're not at co-op, then I will get those from you another time. Please email me, text me. Feel free to ask me any questions you have. Hope you guys are having a great day.